So in the previous video, we conducted an imaginary experiment. We choose 1000 random batteries and classify them into 4 different categories. And those are the results. And based on those imaginary data, we would like to calculate the probability of defective batteries. And that means you can recover the frequency distribution table based on the 1000 imaginary observations, right? And it tells you that among 1000 batteries, these two outcomes, 12 plus 28 outcomes, batteries are defective. So that's 40 out of 1000, which is 4%. This is the final defect rate, overall defect rate, regardless of the supplier, right? So, as you can see, this step is pretty simple. Once you complete the distribution table, then calculating a probability is not a big problem at all. Because what you have to do is to fill in the correct numbers in each category. To do that, you have to apply the correct probability when you make the tree diagram, right? Right. Then now what we are going to do is we are going to track back where those numbers are from, and we are going to extract the essential formula from this idea, this process. So think about this. We at the end we calculate the probability of defective batteries. It was 12 plus 28 divided by 1000, right? That's how we calculate them. And then now we are going to go back where 12 is how 12 is obtained. It is calculated from 2% of 600 domestic batteries. And 28, this number came from this calculation, 7% of 400 imported batteries. In our process, we have already calculated these steps. And then, okay, you know where 2% is coming from. This is a probability given at the beginning from the question. And 7% is also given in the question. But what is 600 and what is 400? They came from this calculation. So we started from 1000 and 60% of them are domestic. So we obtained 600. Similarly, 40% of 1000 was 400. That's why we have 400 here. And then you know what this number is. Again, 60% was given in the question. 40% is also given in the question. So you may replace 2% as this probability, 60% to this probability, like that. Still, one number remains. That is 1000. But it doesn't matter because it will be cancelled out. Numerator, denominator cancelled out. So in the end, this is the essential process formula in our method. So that means instead of drawing the diagram, you may just use this formula, directly calculate the unconditional probability. That is this formula. So I will put it this way. So in the end, we would like to calculate probability of A, but our information is given in these probabilities. So we know probability of B and probability A given B and probability A given B does not happen, right? B complement, right? So and then in the end, based on our earlier derivation, we can write the unconditional probability of A as this, right? Exactly same structure as this, right? Okay, this is it does not have a specific formula name on this formula, but this formula is also intuitive. I will explain that in this way. Suppose that we would like to calculate the overall probability of A, right? In our example, overall defect rate. But our data is categorized into domestic batteries and imported batteries. So there are two groups, and in our notation, you may think the groups are B and B complement. So, and we know defective rate for each group. So probability for each group is known. We know group-wise probability, but what we don't know is the overall probability. Then the relationship is the overall probability is a weighted average, weighted average of those two group level probabilities. But the weighted average is calculated based on the probability of each group. B probability is weight W, B, and the other weight is B W, weight of B complement. So that's how we interpret the relationship between unconditional probability and conditional probabilities. So again, overall probability is weighted average of subgroup probabilities. The weight is determined by the probability of each group, right? So pretty much intuitive, and that's how we interpret this formula. Unfortunately, there is no name for this formula, but you know what we are doing. Okay, then next, again, I'll give you the final results from the tree diagrams, and then calculate the probability of domestic batteries among defective batteries, right? If you put defective batteries aside, how many of them are domestic? Try this, stop the video, and try to answer this question, and resume when you are done. Okay? So, again, these four categories make the full table, probability distribution or frequency distribution table, and we are calculating D given F. Condition is F. That means you don't need these numbers. You only need the number of defective batteries. There are 40 defective batteries in total. Among them, 12 are domestic, 28 are imported. So you can easily find that the conditional probability of domestic batteries among defective ones equals 30%, right? That's it. Again, you see, once you make the full distribution table, calculating a probability is not a problem at all. Just what matters is how you recover the full 2x2 table. And the next step again is to track back and extract the essence of this process. We are going to make a formula which is called Bayes rule. Bayes is the name of a famous statistician. So Bayes derived this formula. So our final product was D given F, which is 12 out of 40. 12 out of 40. And as we did before, we know 12 is from this, 28 is from this, and 600 and 400 from these numbers. And each probability is given, the probabilities are given in the question, but 1000 still remains. Does not matter because it will be cancelled out. 1000 will be cancelled out, and in the end, this is what we actually did. in our process. This form is much more complicated. So the formula has name, Bayes derived it, but idea is simple, you know how to do it. So like formula is more complicated. It has to have another parenthesis here. So Bayes rule, like the main purpose of this formula is to obtain B given A from the information about A given B. A given B and A given B complement is what we have. From there, we'd like to switch the main event and the condition. Then you may apply the Bayes rule, or you may use the tree diagram method. Like, it's up to you. Like, if you are familiar with the formula, that's also fine. But if you wanna but tree diagram method has its own advantage. Like it shows you what we are doing actually behind this formula. So we may connect this Bayes rule to the multiplication rule again, because the conditional probability was defined this way. This was a formula I derived at the beginning of this chapter, right? So denominator, the point is the denominator captures the full size of this condition, and the numerator can be replaced, you can apply the multiplication rule on the numerator. So you put this way. And probability A can be written in a more complicated ways. So you obtain the Bayes rule. This is mathematical way of derivation, but you know, I'm telling you, like these 3 steps to derive the Bayes rule, but you don't need to understand the derivation. Just try to understand the tree diagram method. Okay, so in the next video, I'm going to give you another example, and we'll keep working on the Bayes rule, another example to apply the Bayes rule. See you later.